All right, so what we do today is pretty much going to be a review. Right? You learned about work energy theorem in Science 10. And since we have a shortened class today, we probably won't get much further into it than to review all the stuff you already know about it from Science 10. Okay? So, first off, we have to understand what work is. Okay? Anybody remember what work is from Science 10? Besides a four-letter word. Okay, if I do work on something, what am I changing about it? I could be changing its position. Okay, if I was changing its position, let's say, because here's an example of work. Okay, if I lift something up, I'm not going to pick something heavy because I'm old. Okay, so if this is sitting on the desk and I change its position by this much and hold it here, okay, I've done work. Not only have I changed this thing's position, but I've given it what?
Energy.
Right. What kind of energy have I given it? Potential energy. Right. Because if I let it go.
I guess if you're going to drop it.
Yeah, exactly. But I mean, it doesn't have any kinetic.
Work is though? I thought it was applied energy, but I can't remember.
Nope, it's not applied energy. It's a change in energy. Okay. If I do work on something, I change its energy. I change its mechanical energy to be specific. Mechanical energy is the sum of an object's potential and kinetic energies. When I do work, I am changing one or the other or both types of energy. In Science 10, you only had to deal with situations where either potential energy was changed or kinetic energy was changed, and that was it. In Physics 20, you will deal with situations where both types are changed. It's not any different. Okay? We just have to keep track of kinetic and potential at the same time. It really doesn't make it any more difficult than, let's say, the conservation of energy roller coaster questions you would have done in Science 10. Okay? So, what is work? Work is a change in mechanical energy. Okay? That is the definition of work. Right? A change in mechanical energy. If I do work on something, I will either change its potential energy by raising it above the ground, or I will change its kinetic energy by making it go faster, or I will change its elastic potential energy by changing its shape and having it have the ability to rebound back to its original shape, like compressing or stretching a spring or drawing a bow, okay, or something like that. All right, understand the relationship between force and work. All right, work is when you exert a force through a distance. Okay? So if I exert more force on an object through the same distance, I should do more or less work? More, yeah. Okay. If I've got just one of those little carts like we've been using in our labs, and I give it just a gentle push over a 5 centimeter distance, it's not going to go very fast. But if I wind up and smack it, okay, over a 5 centimeter distance, it's going to go faster because I exerted more force. Okay, so the more force I exert, the more work I'm going to do. Or I exert the same amount of force, but over a longer distance. That'll allow me to do more work too. That's the principle behind the inclined plane. Okay? An inclined plane allows me to do the same amount of work as someone who lifts something using less force over a greater distance. Okay. Everybody with me there? Okay. All right, and then learn that depending on the situation, work and energy can be equal. That's the work energy theorem, because when I do work, I change energy. If it's a perfect system, which is what we're going to be dealing with most of the time, okay, then the amount of work I do will be equal to the amount of energy that I put into that system. Okay. All right, is that ringing a bell? Okay, because we're going to be bringing in a lot of stuff that you know, and then one or two little things here that are going to be a bit different. All right, so when you do work, you exert a force through a distance. You can't do work any other way. Okay? There has to be a force, there has to be movement, otherwise there's no work. Okay? It's impossible to change something's energy, mechanical energy, if there's no movement. Okay? It is possible to change something's thermal energy, but that's different. Okay? All right, so in this situation, this person is pushing the stalled car, okay? And they're pushing it through a distance. Are they doing work? Okay. The car's moving, but the car's not accelerating. They're pushing it at a constant velocity. Are they still doing work? In the perfect physical world where there would be no friction, they would do no work. Okay? There would be no work at all done there. Okay? Because it doesn't require any force to move something at a constant velocity in the perfect world, does it? That's Newton's first law. Okay? But in the real world, I have to do work because I have to overcome what force? Friction. Yeah. Okay? Now, where's the energy going? Because if I'm pushing something at a constant velocity along a level surface, I'm not changing its kinetic energy because it's not going any faster. And I'm not changing its potential energy because it's not getting any higher. Where's all my energy going? Where's all the work I'm doing going? Are there other forms of energy that might be being changed other than the mechanical energy of the car? When the car rolls along the ground, does it make sound? Is sound a form of energy? It is. Okay? So what would happen here, guys, is if I'm pushing that car, but I'm not making it go any faster, and it's not uphill, I'm not doing any work on the car because the car's energy isn't changing. But the energy of the system and its surroundings are. I'm putting sound into the surroundings. There's going to be some heat as well between the tire and the road. Okay? All of those are forms of energy. That's where my work is going. Okay? I'm still doing work. I'm just not changing the mechanical energy of the car with my work. Okay? Now, if I push really hard and I accelerate the car, then yes, then I'm doing work on the car because its speed will increase, and that means there's been a change in the kinetic energy of the car. Okay? Everybody all right with that? Okay, are these four girls doing any work? Yes, the rock's not moving. Are they doing any work? Not on the rock. If they keep pushing, will they get tired? Why? They're not doing any work. Doing work on the ground. Well, but the ground's not moving.
If you're pushing it really hard, can't you like hear rocks moving and stuff on the floor?
Oh, if I can hear stuff moving, something's moving. I'm really messing with it. Okay, think about this. This is how isometrics works. How many people have heard of isometrics? It's a type of workout. Okay? Isometrics is a workout where you don't move, okay, but you hold something. So if you've ever seen like the people that do the strongest man stuff and they hold like the giant metal bells out at like arm's length like this, that's isometrics. I'm still doing work. I'm holding those bells. I'm not changing the energy of the bells, but I'm working against the force of gravity trying to pull those bells. Okay? I still expend work. It pulls on me, I pull back on it. I still have to do work. Okay? And the same thing is happening with them. If I push on the wall, okay, pretend that the wall didn't make that sound because I'm huge. Okay? But if I push on the wall doesn't move, but I can push and push and push, and I'll get tired. Because when I push on the wall, what does the wall do? Right? What do my muscles do? They contract. There's movement. Okay? There's where the movement is. The wall's not moving, but when the wall pushes back on me, my muscles get shorter. There's the distance over which the force is exerted. Okay? Now I have to brace myself against that force so I don't move. Okay? But part of me did. Okay? And I'm going to keep it that way, which is going to expend energy. Now that energy isn't going to do anything except turn into heat, make me hot and sweaty and tired. Right? But it's still work. Okay? So work, I can do work without like seeing the results of it, but true work results in something happening. Something is going to move. Okay? Now, units for work are a Newton meter. Why are they a Newton meter? Well, because when you do this formula, force times distance, you are multiplying newtons by meters. Thus, Newton meters. You'll never write it like that. Okay? Technically, it's a kilogram meters squared per second squared. Because a Newton is a kilogram meter per second squared, so a joule would be a kilogram meter squared per second squared. You'll never write it like that. Joules. Okay, that's all you have to remember. All right. What if I use an angled force? This goes back to the people pushing the rock and the rock doesn't move. If I'm rolling this luggage carrier along the floor, okay, I'm pulling it at an angle, but it's moving horizontally. Okay? Am I doing work? I am, but not in the direction that I'm exerting the force. There's no change in energy along this vector. This is the way the cart is going. So is all of the force I'm exerting doing work? It's not. What part of it is, horizontal or vertical? Horizontal, right? The vertical is not doing anything. I'm not lifting the luggage. Luggage is not coming off the ground, okay? I'm pulling the luggage this way, okay? So if I pull the luggage this way, this is the direction in which the work is done, which is where the change to the work formula is going to come in. Work truly written is this: force cos of theta times d. We've never had to use the cos of theta part because the force and the displacement were always in the same direction. But now we know it's possible to pull something one way and have it go a different way, which means not all of my force is doing useful work. Only the horizontal component of it, in this case, is doing useful work. Okay. Does that make that formula like ludicrously hard? Not at all. Okay. It just adds a little thing in there. Okay. Okay. So if this is what I'm doing and the cart accelerates, what kind of energy am I changing about it? Kinetic, right? I'm changing its mechanical energy because kinetic is part of mechanical, okay? But specifically, I'm changing its mechanical energy. Because this is a level floor and I'm not lifting the suitcases, I'm not doing any changing of the potential energy. Okay, it's not getting higher off the ground, so this would just be a change in kinetic. All right, so if we want to find the work done by this 45 Newton force that I'm using to pull the luggage carrier, okay, at a 50-degree angle for 75 meters, I just have to plug into my new formula here. Force, 45 newtons, times the cos of 50 times 75 meters, right? So I would do 2.17 times 10 to the 3 joules of useful work. Okay? Whatever the vertical component of that force is isn't doing anything because there's no movement in that direction. Everybody okay with how that one works? All right, weightlifting. So if I want to do the bench press, okay, simple weightlifting exercise. I want to do the bench press, and I have a 710 Newton barbell, and I want to lift it at a constant velocity. How much force do I have to exert? 710 newtons. I'm moving it at a constant velocity. Net force is going to be 0. So it weighs 710 newtons. I have to push with 710 newtons. All right, so I push with 710 newtons, and I lift this thing 0.65 meters. Can I calculate the amount of work done? Right, just force times distance, right? Okay, so work is F cos of theta times d. Now, my force and my displacement are in exactly the same direction. So what's theta? 0. 0. All right, that's good. Cos of 0 is 1. Right? So I don't have to do anything with that. I just have to go 710 times 0.65 meters. And I'll have the amount of work done to lift this thing up. So times 0.65. All right, so I'm going to do 462 joules worth of work to lift the barbell. Now, here's what lots of people do when they do the bench press. They do it wrong. They put a bunch of weight on the bar and they push as hard as they can and they get it up. And then they go, and they just lower it back down like right away. They basically just let it drop and the spotter has to like hold on for dear life. Okay? Are you getting a full workout if you do it that way? No, you don't want to let 710 newtons accelerate towards your chest. Okay? That's how you end up with broken ribs. You lower it slowly. And if you want to do this the right way, you push up slowly and you lower slowly. Because if you do it that way, you're exerting 710 newtons the entire time. And you get a better workout and you get better results. If you just push it up and then let it drop, okay, you're missing half the workout. Because you're not using that force all the way down, just at the very end. Okay? So we don't want to do that. We want to use it over the full distance. That means I do work no matter whether I'm lifting it or lowering it. Okay? Because I have to resist the 710 newtons. If I don't, I'll die. Okay? I have to lower it slowly. I have to exert 710 newtons up. All right. So when I lift the barbell, it gains 462 joules worth of potential energy. That energy has to go somewhere. When I lower it, it's going to lose that energy, agreed? That's why I have to push up on it. I have to let it change the shape of my muscles while I lower it down, okay, so that it doesn't convert all of that into kinetic energy, which can hurt me. Okay? I need to convert it into heat and grunting and whatever else other forms of energy are involved, okay, as I lower it down. Okay? Everybody follow me there? So, how much work is done when I lower it? Can I use this formula again? Okay, so when I lower the barbell, okay, I'm going to go F cos of theta times D. But now that's going to be 710 times what angle? I'm exerting the force upwards. The barbell's moving downwards. What's the angle? Okay, so here's the way it's going, or here's the way I'm pushing, here's the way it's going. What's my angle? 180 degrees. Punch into your calculator. What's the cos of 180? Not 1. Negative 1. Okay, so now I've got 710 newtons up. That's positive. Times negative 1, because it's moving the other way, times 0.65, I get negative 462 joules. That makes sense. The barbell has lost that energy. I lowered it back down to where it started. It doesn't have that energy anymore. It did that work on me. That's why it's mislabeled. We call it working out. Well, when I lifted it, it was working out. But when I lowered it, it was working in. Okay? It gave me that energy back, sort of. Okay? I had to resist it when I lowered it. Okay. Everybody okay with that idea? All right. Okay, so here's what we have to remember about work energy theorem. Okay, in order to do work, you have to have energy. Okay, this is kind of a chicken and the egg kind of an idea here, but if work is a change in energy or a transfer of mechanical energy, I have to have energy to give, or I can't do work. Okay, this isn't like credit cards, okay, where I can have no money but still spend it. Okay, in this case, I can't spend what I don't have. I can't change the energy of something without giving some of my own energy to it. Okay? Work is a change in energy. Okay? So in order to do work, you have to have energy. right? So, you know, when it snows really bad and your, you know, mom or dad tells you to go out and shovel the driveway and you tell them, I can't, I don't have any energy. If that were true, that you actually didn't have any energy, you'd be dead. But, I mean, technically speaking, if you don't have any energy, you would be incapable of shoveling the driveway because that's work. You're changing the position of the snow. You're piling it up on the side. That's work. Okay? You have to have energy to do that. Right? So that's the work energy theorem. It basically says energy is needed to do work because work is a transfer of energy. Okay? If work is done, the object being worked on gains that much energy. And then we have these formulas here. Okay? Kinetic energy is 1/2 times mass times speed squared, and potential energy is mass times gravity times height. Hopefully those are somewhat familiar.
We're talking about shoveling snow. Probably gonna talk about this, but would it be like indirect, like work into the snow? Because you're putting it into the shovel, right?
Yeah, I mean, there's going to be some energy loss, right? You hear the shovel, that's friction, that's sound, it's a form of wasted energy, right? But when I move the snow, I change its velocity, right? It kind of arcs a little bit or whatever, okay? And eventually it ends up on the pile.
Yeah, I was asking if it's like, because you're not picking up the snow and moving it, right? You're using something in between, so is that like an indirect sort of interaction, or?
No, it's, I mean, I'm doing work on the shovel because the shovel is connected to the snow, so my force is still the thing that's doing it all. Without me, the shovel is useless.
Yeah.
Yeah, the shovel can't do anything by itself, right? So it's still me, but I'm just using a tool. Yeah, the work is done through the tool or with the tool, but it's still done by me. I'm the source of the energy. Yeah. So I guess in that way you could say it's kind of indirect, but it's still a transfer of energy from me to ultimately the snow. All right, and then the other thing we have to remember is about mechanical energy. Okay, so mechanical energy is an object's kinetic and potential energy. It's the sum total of those two types of energy. So when I do work, I could be changing one or the other or both. And that's what we'll be looking at, okay, soon. Okay. But we didn't get to this thing that I wanted to do the other day, and now I'm going to do it. The everybody jumps farce. Because if everybody jumped, we could totally knock the Earth out of orbit. Oh, it's not on here. There it is. Okay, so we want to see what effect having everybody jump at the same time would have on the Earth. So this is a bit of Newton's third law, but it's also a bit of work energy, which is why I wanted to do the work energy stuff before we got to this. Right? So getting everybody to do this would end the world. Totally. Not because it knocks the Earth out of orbit. It's completely a practical problem. The world's population is 7 billion or close to it. You have to put 7 billion people shoulder to shoulder in one place on Earth and have them all jump together. I don't know how you get them there, or get them home, or take care of everything that happens while they're there. Food, water, sewage, garbage. Yeah, this would be a problem. Okay, huge problem, but not because everybody jumped. All right, so at the start of the scenario, the entire Earth's population has been magically transported together into one place because we have no idea how the hell we get them there other than magic. Okay? All right, so they're all together in one place. The crowd is so large that it takes up an area the size of Rhode Island, the smallest of the 50 states. Okay? There's no reason to use a vague phrase like on an area the size of Rhode Island. We're just going to say we're going to put them all in Rhode Island. That's where the jump is going to occur. Okay? We're going to put them all in Rhode Island, and everyone standing shoulder to shoulder, the whole state will be covered with people. Okay? That's how many people. There's a lot of people in the world. Okay? All right. So we're all in Rhode Island, whole Earth population. There's our crowd. Okay, everybody there. We've timed this so that at the stroke of noon, everybody will jump. What's the problem with that?
People can jump higher than other people and have slower reaction time and stuff like that, so you might want to jump at the same time.
Yeah. Okay. And what if my watch is different than yours? Okay. Like, I mean, you look some people's watches, they're like 4 or 5 minutes difference. Okay. Like my wife likes to have the clock in her car like 9 minutes ahead. Throws me off every time I get in there. Okay. Just some people don't have their watch set the same way as everybody else, so there could be that problem. Okay. There's also the problem of some people are going to jump better than others. What about people in wheelchairs, infants, old people who can't jump anymore, like me? Okay, like there's all these issues with getting everybody to jump. They're practical problems, but they're still problems. Okay, I'm not going to get everybody to jump in the same way Nike didn't get everybody to run. I mean, I don't know if you guys saw, but like years ago, Bill Nye was on like Dancing with the Stars. They showed him running in that ad. That had to have been CG because the guy could barely move. He's so arthritic. Okay, so there's that problem. Not everybody's going to be able to jump. Okay, all of that. So we're just going to assume, because we magically transported everybody there, that we're magically going to get everybody to jump at the same time. Because how do you get a crowd that goes over the horizon? Okay, I mean, picture this, guys. Like, Rhode Island is a state. It's like, you can't see all the parts of Okotoks from here. How do you see the whole crowd? And more importantly, how do you get the whole crowd to do something at once if it's that big? Okay, you can't use like a starter's pistol. It would take the sound a half an hour to travel to the other side of the crowd. Right? There's all these practical problems with getting everybody to jump at the same time. You could use like the text message thing, but not everybody has a phone. Okay? And there would be another problem with having 7.5 billion phones occupying the same network. Okay? That would be a problem too. So, all right. So as discussed elsewhere, it doesn't really affect the planet very much. Okay? The planet outweighs us by a factor of over 10 trillion times. Not you and me. The whole Earth's population is over 10 trillion times smaller than the population or than the mass of the Earth. Okay, so on average, we humans can vertically jump maybe half a meter on a good day. So this was the other problem. Some people jump higher than others. Okay, even if the Earth were rigid and responded instantly, it would be pushed down by less than an atom's width. Okay, nothing basically. Okay, next, everyone falls back to the ground. Technically, this delivers a lot of energy into the Earth. It means a lot of people falling back down to the Earth. Okay, but it's spread out over the entire state of Rhode Island. So that's a pretty big area. Okay, so it doesn't do much more than leave footprints in a lot of gardens. Okay, a slight pulse of pressure spreads out through the North American continental crust and dissipates with little effect. It would be kind of like rolling thunder, maybe. Okay, something like that. All right. The sound of all those feet hitting the ground creates a loud, drawn-out roar which lasts many seconds. Eventually, the air goes quiet. Seconds pass. Everyone looks around. It's awkward. We're all standing there, and we've all just jumped, and now what? Okay, so why did we do this? Is this Rhode Island? Okay, there are a lot of uncomfortable glances. Someone coughs and freaks everyone out because it's COVID. Okay, and then the people are like, okay, well, now I want to go home. You magically transported me here. Now I have to get home. All right, cell phone comes out of a pocket. Within seconds, the rest of the world's 5 billion phones follow. All of them, even those compatible with the region's cell towers, are displaying some version of no signal because the cell networks collapse under the unprecedented load. Outside Rhode Island, abandoned machinery begins grinding to a halt. Think about this. France generates almost all of its electrical power using nuclear power. The people that are supposed to be monitoring that are in Rhode Island. Ever hear of Chernobyl? Okay, that's true everywhere. Everything that's supposed to be monitored 24/7 has been completely abandoned for everyone to jump. So now stuff's happening. Okay, these are like really bad scenarios because whole cities could burn to the ground as a result of this. Because where are the firemen? They're in Rhode Island, jumping. Okay, I mean it's tongue in cheek, but it's also true if this would actually happen. All right, so the TF Green Airport in Warwick, Rhode Island handles a few thousand passengers a day. Assuming they got things organized, including sending out scouting missions to retrieve fuel, they could run at 500% capacity for years and not make a dent in the crowd. I mean, we're talking about an airport that could now handle, let's say at best, 100,000 passengers a day. That doesn't put much of a dent in 7 billion people. Right? Okay. So, the addition of all the nearby airports doesn't change the equation very much, nor does the region's light rail system. Crowds climb on board container ships in the deepwater port of Providence, but stocking sufficient food and water for a long sea voyage proves to be a challenge. Rhode Island's 500,000 cars are commandeered. Moments later, I-95, I-195, and I-295 become the sites of the largest traffic jam in the history of the planet. Most of the cars are engulfed by the crowds. It's like something out of the early seasons of The Walking Dead. Okay? That's what it would look like. It would be chaos. Okay? All right, so some make it past New York or Boston before they run out of fuel. Since the electricity is probably not on anymore, there's no way to get a gas pump to work. So you can't refuel, but that's fine. You can just steal a car because there's no police around. They're all in Rhode Island jumping. Okay, so you just get another one. Okay, the edge of the crowd spreads outward into southern Massachusetts, Connecticut. Any two people who meet are unlikely to have a language in common, and almost nobody knows the area. I mean, imagine if you just came here from East Timor and now you're in Rhode Island. You don't know the lay of the land. You can't read the signs. Okay, you're pretty screwed. Okay, so the state becomes a patchwork chaos of coalescing and collapsing social hierarchies. Walking Dead. Okay, right? So there'd be like Negans everywhere. It'd be really bad. Okay. So violence is common. Everybody's hungry and thirsty. Grocery stores are empty. Fresh water is hard to come by, and there's no efficient system for distributing it. Nobody has mentioned the feces problem. It can be, pretty nasty. You probably didn't bring a lot of porta potties along, things like that. Okay. Within weeks, Rhode Island is a graveyard of billions. Okay. The survivors spread out across the face of the world and struggle to build a new civilization atop the pristine ruins of the old. Okay? Our species staggers on, but our population has been greatly reduced. Earth's orbit is completely unaffected. It spins along exactly as it did before our species-ending jump. Okay? But at least we know. Yeah.
Why can't they just magically put everyone back? Like
Because there wouldn't be any fun in that. I don't get to be sarcastic if they do it that way. All right, so we talked about some of these questions already. What are some of the problems with synchronizing everybody's jump? Well, everybody's watch has to be synchronized. You have to have some sort of signal that everybody would receive at exactly the right time. It can't be acoustic. It can't be visual. Okay, it would have to be some sort of electronic thing that everyone could receive. But then you've got the cell network problem. So there'd be really. What's that?
What about blind people?
Well, no, if you had like a device that had like it vibrated and made noise like a phone, okay, if everybody had one of those, then there would maybe be some way to do that, provided you could support the network demand on that, right? So there'd be a huge problem with synchronizing 7.5 billion people. I mean, come on, it's hard for me to get 25 of you to do everything at the same time, okay? Imagine what it would be like to get 7.5 billion people to do something at the same time. Okay. Calculate the total mass of the Earth's population, assuming the average mass of a person is 65 kilograms. Okay, so 65 times. And we'll just go with 7 billion. We'll say 7 billion. Yeah. Okay, so there's the mass of every person on Earth. 4.55 times 10 to the 11 kilograms. Okay, calculate the total gravitational potential energy of the crowd when they are at the maximum height of their jump. So we said everyone would jump about a half a meter, right? So that's m times g times h. So that number, okay, are 4.55 times 10 to the 11 times 9.81 g times the height, 0.5 meters. Okay, 2.2 times 10 to the 12 joules. That's a lot. That's a lot of energy. Okay, think about it. Let's see. That's faster. Okay. Energy in 1 kiloton of TNT.
Kiloton?
Okay, this is just shy of the energy in 1,000 tons of dynamite. Okay, so if you imagine I had 1,000 tons of dynamite and blew it up, that's about the same amount of energy. It's 4.184 times 10 to the 12 joules is the amount of energy that is in 1 kiloton, 1,000 tons of TNT. Okay? There's a number you'll never need to remember. All right, so anyway, that's a lot of energy. That's the size, that's the same output roughly as the bomb that was dropped in Hiroshima. Okay, so it's a lot of energy. Okay, determine the kinetic energy of the crowd as they strike the earth after their fall. Okay, so if I jumped up and got this much potential energy, when I come down, I should have that same amount. I just turn it into kinetic from potential. As I fall, that's what always happens. Anytime something falls, the potential energy gets turned into kinetic energy. So that's how much energy is going to be delivered to the earth, okay, when everybody hits it. All right, so law of conservation of energy says that energy can't be created or destroyed, but the kinetic energy of the earth will be less than that amount of energy. All right, and that's because the earth is not a rigid ball. Okay, when people land, they're going to compress the ground, there's going to be sound, there's going to be heat. It's not all going into moving the earth. All right? But we're going to say, just for argument's sake, all of it ends up going into the earth. Okay? So we want to determine, so we've already determined, the maximum kinetic energy of the earth as a result of the crowd hitting it. Calculate the maximum speed that will change the earth's speed by. Okay? So now we're saying that this number that we just calculated is now going to be the earth's kinetic energy. Okay? So here's what we're saying. Okay? That number is EK, that one that was in my calculator. That's going to be the kinetic energy the Earth is going to receive. Okay? What's it going to do to the Earth's speed? All right, so how do I find the Earth's speed with this formula? What do I have to do with the half and the m? Okay. And then what? Okay. So we are going to have, what did we say? It was 2.2 times 10 to the 12 joules divided by 1/2 times the Earth's mass, 5.98 times 10 to the 24 kilograms. That's the Earth's mass. So put that in. Square root of answer divided by 0.5 times 5.98 E24. Okay, so the Earth's speed will change by 8.6 times 10 to the minus 7 meters. So 9 micrometers per second. I don't think that's going to knock us out of orbit.
I think that's really close, right on the cusp.
Right on the cusp, absolutely.
Yeah.
Yeah.
We just need like 10 more people.
All right, so there you go. Okay, we don't have to worry about that. It's not going to happen. Same as everybody running in the same direction is not going to reverse the spin of the Earth. Okay, none of that stuff is true. None of that stuff will work. Okay,
I think it would work.
but it comes down to Newton's third law and some work energy theorem stuff. That's why we did that today, kind of for entertainment more than anything else. Okay, all right. After Easter, okay, you've got these things coming up. Okay, your Newton assignments are due on April 13th. Your unit exam will be April 21st. Okay, we're going to have another lab when we come back as well on conservation of energy. Okay, so just be ready for that. Okay? All right, if everybody can clear off their desks, I'll come around and wipe them down.